So we continue with magnetism, and now we are on the point the magnetic field of the earth. So we are now going to have some kind of evidence. Okay, we are trying to find out some evidence that there is a magnet inside the earth. That's why the earth's magnetic field. So in fact we can say that if this is the earth, it is seen that if this is the north pole over here, this is the north pole and this is the south pole, it will be seen that inside over here is a big magnet which has got the south pole of the magnet over here and the north pole of the magnet over here. So this is a very big magnet right from the north pole to the south pole, such that the south pole of the magnet is at the geographical north and the north pole is at the geographical south. And this also explains us that why a magnetic needle, when I place over here, will be resting in the north-south direction. It will always be in the north-south direction over here, because the north pole over here is attracted by the south pole of the magnet and the south pole is towards the north. So that's why you'll always find that the Earth's north pole and south pole are attracted. The Earth's south pole of the magnet is attracting the north pole of the normal magnet or the needle, magnetic needle, which we are having in our hands, or even a bar magnet. So our earth itself has a magnetic field and it behaves like a magnet. The existence of earth magnetic field is based on the following facts. First, a freely suspended magnetic needle always rests in the geographical north-south direction. So that's the first point. As I told you, it will be when I freely suspend a magnet, it is going to rest in the north-south. Why is it acting in the north-south direction? Because the north pole of the magnet is attracted by the south pole of the earth magnet, and the south pole of the earth magnet is resting in the north pole of the earth, and that's why it is this we consider as the north pole. Okay. Secondly, an iron rod buried inside the earth along north-south direction becomes a magnet. Third thing, neutral points are obtained on plotting the field lines of a magnet where the net magnetic field is zero. And fourth is a magnetic needle rests on its geometrical axis, making different angles with horizontal when suspended at different places on the earth. So let's study these points one by one in detail. First one, a freely suspended magnetic needle always rests in the geographical north-south direction. When a magnetic needle or a magnet is suspended such that it is free to rotate in a horizontal plane, it always rests indicating the geographical north-south direction. But the north pole of the magnet will point towards the geographical north, but only when there is a magnetic south pole attracting it. So yeah, that's the theory that okay, if this particular magnet is resting at the north pole over here, so it means north-south direction, that means there is some magnet over here which is attracting the north pole over here. So that means some south pole is of a magnet is here which is attracting the north pole of the magnet. So that's why similarly the south pole of the magnet will point towards the geographical south when there is magnetic north pole attracting it. Therefore, we can assume a magnet inside the earth which must have its south pole in the geographical north and north pole in the geographical south. The next is an iron rod buried inside the earth along north-south direction becomes a magnet. If an iron rod is buried few meters inside the earth, keeping it along north-south direction, after some days it is found that the rod becomes a weak magnet. It is possible only if the earth itself behaves like a magnet, because only then it could have been possible that it is coming in contact with the magnetic field of the earth magnet inside, and that is why there is an induced magnetism produced in that particular magnet. The third point is neutral points are obtained on plotting the field lines of a magnet. Now this neutral point we are going to understand much better when we see the last figures which are there, maybe in the next video. But yeah, there are certain figures which you are going to draw for what will happen when a magnet is placed in a magnetic north-south direction or in a that direction. So we'll study that. Fine. So if a magnet is placed in a horizontal plane with its north pole facing towards the geographical north, and the magnetic field lines are plotted, we obtain two neutral points on either side of the magnet on its broad side on position. Similarly, if the magnet is placed in the horizontal plane with its south pole facing towards the geographical south and magnetic field lines are plotted, we obtain two neutral points, one on either side of the magnet on its end on positions. At each neutral point, the resultant magnetic field is zero. That is, if a compass needle is placed at the neutral point, it rests in any direction. So, it is seen that whenever any magnet is placed in such a way that the north pole of the bar magnet, is pointing towards the north of the Earth, okay, the Earth magnet, then it will be seen that if it is north pole is towards the north, then there will be neutral points formed in the these sides, okay, यहाँ पे और यहाँ पे ये दो point पे neutral points बनेंगे. But if this is such that this is the south pole and this is connected to the north pole, then south pole यहाँ पे है और north pole of the earth, यानी north direction is over here, then the neutral point will be here and here, means it will be here and here. So that particular points, the neutral points are such that अगर हम लोग वहाँ पे कोई भी magnetic needle place करेंगे, तो the magnetic needle will not rest in a particular position. So that is why we find that those are points where the net resultant forces of the magnetic fields over there is zero, and this is also because of the property of magnet that they do not intersect each other. The magnetic field do not intersect each other. So when they are not intersecting, that means there will be a point where both are getting diverged, or they are going to be compressed in such a way that it is allowing them each other to give some space, और वो दोनों के बीच में जो boundary बनेगा, at that particular point will be the neutral point. So if the reason for zero resultant magnetic field at a neutral point is that magnetic field produced by the magnet is neutralized by some other equal and opposite magnetic field. So magnetic field of the earth and magnetic field of this are getting cancelled over there, and that's why there is a neutral point which is formed over there. This other magnetic field is actually the horizontal component of the Earth's magnetic field. So mainly the other magnetic field in which that particular thing was placed in is nothing but the Earth's magnetic field, and that's what we are going to have is the diagrams, that is figure number 10.9 and 10.10. So these two figures are very, very important, which we are studying in the later part of the chapter. And the fourth and the last thing is that a magnetic needle rests making different angles with the horizontal when suspended at different places of the earth. So it is seen that if I place the magnetic compass, this is the magnet, it will find that the magnetic compass will be resting like this over here, उसके बाद ऐसे, फिर ऐसे, this is north and yeah, that's right. So ऐसे, फिर ऐसे, फिर ऐसे, फिर ऐसे, फिर ऐसे. So they will be always in different angles. Okay, they will be always in a different angles. What you're going to make with the earth. So otherwise, if it were to be always north south, every time it would have formed like this only. It should have gone like this, north south. But ऐसा नहीं होता. It is at different angles. It will be like this, and it will be like this over here, then like this over here, then like this over here. तो ये ऐसे angles पे क्यों है? Because it is attracted towards the magnetic poles present inside the earth. So, if a magnetic needle is suspended such that it is free to rotate in a vertical plane, it is taken around the earth through its geographical poles, we find that at two places, magnetic needles becomes normal to the earth's surface. That is, they become vertical. Okay, so at this point and at this point, they are going to become exactly vertical. These points are called the magnetic poles, Earth's magnetic poles. At two places, it becomes parallel to the Earth surface, that is, becomes horizontal, that is basically at the equator. So at the equator they are going to become like this, and at these poles are going to become at the straight line like this. These points lie on the Earth's equator, magnetic equator. At other points, it rests making different angles with the horizontal as shown in the figure 10.6. It implies that the Earth itself has a magnetic field. Two places where the magnetic needle becomes vertical are called as the magnetic poles. The lines joining the places where the magnetic needle becomes horizontal is called as the magnetic equator. Conclusion. So what we conclude by all these 4 points is that on the basis of the above facts, it can be concluded that the Earth behaves as if it is a huge bar magnet is present at its center with its magnetic south pole in the geographical north and the magnetic north pole in the geographical south. Actually, the geographical poles do not coincide with the Earth's magnetic poles, but they are somewhat displaced. The magnetic axis of the Earth makes an angle of 17 degrees with the axis of rotation of the Earth. The magnetic pole, south pole of the Earth is at Canada at a distance nearly 2,240 kilometers from the geographical North Pole at 70.75 degrees north latitude and 96 degree west longitude. While the Earth's magnetic North Pole is at a distance nearly 2,240 kilometers from the geographical South Pole at 73 degrees south latitude and 1,155 degree east longitude. It has been experimentally observed that the position of these poles are not stationary, but they gradually change over a long period of time. Anyways, it's not important for you to learn these longitude and latitudes and things like that. You can just for your understanding that yes, the magnetic field that is not exactly on the North Pole and the South Pole, they are slightly drifted. That is near Canada over here, that is 2,200. The distance between this and this is equal to 2,240 kilometers. Okay, so that is the distance between the actual North Pole of the magnet and the actual North Pole of the Earth. So now about the magnetic field lines of the Earth. It is a limited space. In a limited space, the magnetic field lines of Earth are parallel and equidistant to each other, as shown in figure 10.7b. They are, that is something similar to, I'll just erase that. So they are basically lines like this. Parallel lines over here, which are the magnetic fields, which are said to be as the uniform magnetic fields. So in a limited space, the magnetic field of Earth are parallel and equidistant to each other, as shown in figure 10.7b. They are always directed from the geographical south to the geographical north. They are horizontal at the magnetic equator and vertical at the magnetic poles. But at any other point, they are inclined to the horizontal. They are always inclined to the horizon for any other pole. But yes, at the center, and at this one, they are going to be this way. Then at the magnetic equator, they are horizontal and they are vertical. Horizontal over here, and vertical at the magnetic poles. The magnetic field lines of the Earth are normal to the Earth's surface near the magnetic poles and parallel to the Earth's surface near the magnetic equator. So when you are near the equator, here is magnetic equator, not the equator of the Earth. Near the magnetic equator, the field lines will be parallel, okay, whereas in case of the north and south poles, that is the magnetic field lines are normal to the Earth's surface. Now if you want to plot the uniform magnetic field, you can easily do this by taking the compass, and what you do is that you hold the compass over here like this and see what is the point over here. Mark this point here and here like this, then place the magnetic compass again over here, and then again mark the next point. So if it is coming like this, then you are just going to point here. Now you mark another, again you put it over here. Suppose now it is showing you like this, then you mark it over here. Now suppose you are doing it this way and it is going you this way, you automatically mark it over. So you know that the magnetic field line is like this. But if it is like this, going to come like this, then you know the magnetic field lines is a straight line like this. So if I want to trace the path of the magnetic field, I just need to place the magnetic compass one after the another at the points, so that I can trace out the direction in which the magnetic field is passing. So Earth's magnetic field is a uniform in a limited space. Experiment where you can plot uniform magnetic field lines on the Earth as follows. Experiment: fix a sheet of paper on a drawing board by means of brass pins. Place a small compass needle at position 1, and looking from top of the needle, mark 2 pencil dots exactly in the front of the ends of the needles. Then move the compass needle to position 2 in such a way that one end of the needle coincides with the second pencil dot. Mark the position of the other end of the needle with the dot. Repeat the process for moving the compass needle to point 3, 4, etc. To obtain several dots on joining the different dots, we will get the straight line. Thus, one magnetic field of the Earth is traced. Repeat the process starting from the different point and trace out another magnetic field lines. In this manner, draw several magnetic field lines starting from the different points. Label each line with an arrow from the south pole of the needle towards the north pole to indicate the direction of the magnetic field. Figure 10.7b shows several magnetic field lines so obtained. It is noticed that the lines do not intersect each other. They are parallel and equidistant. They are directed by geographical south and geographical north, that is the direction in which the magnetic needle suspends freely in a horizontal plane rest. So this is how we are going to plot a uniform magnetic field. Okay, again, not so important to learn, never ask a question regarding this thing, but next thing what we are having are very, very important. So the next what we are having is all very important parts. So let's see. Plotting of non-uniform magnetic field of a strong bar magnet at neutral points. The magnetic field around a bar magnet or a horseshoe magnet is non-uniform. The magnetic field lines in a non-uniform magnetic field are not equispaced and parallel, but they are curved, either converging or diverging. The closely spaced magnetic field lines at a place represent a strong magnetic field lines at that place, while the widely spaced magnetic field lines at a place represent the weak magnetic field at that place. So if I see that there are too many dense number of magnetic field lines in a particular area, that shows that it is a strong magnetic field. But if they are spaced out and not so dense amount of field lines, then I can understand that these are weak magnetic fields. Figure 10.8 shows the non-uniform magnetic field lines due to a bar magnet, a horseshoe magnet, two unlike poles facing each other, and two like poles facing each other. So these are very, very important diagrams. They do ask questions directly based on this, that draw the field lines for a bar magnet or for two magnets placed in such a way that their like poles are. So first thing is that you have got a bar magnet. So it is a bar magnet, it is definitely going to be like this. So the field lines will be like this. Of course, the direction will be like this, away coming here. So this is a bar magnet. In case of a horseshoe magnet, so in a horseshoe magnet, now this is the north pole and this is the south pole. So of course there will be a field lines traveling from here to here. Okay, so there will be field lines which will be going from here and coming back over here. So these are the field lines for a horseshoe magnet. Now when there is a bar magnet having a north pole coming in contact with the south pole over here, there will be the field lines coming directly from north pole to south pole like this. So this will be the condition when the north pole and south pole are directly placed in front of each other. And another one will be in such a case that there will be a north pole in front of a north pole or a south pole somewhere. In this case, this is going to go like this. This is also going to go like this. This will go like this. This will go like this. They are not intersecting each other. Similarly, one will go like this. 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 So this will be repulsion. So the repulsion takes place in this order, that the field lines are going to be spread it out towards this way, because they are actually going to travel to the south here, so they are not going to intersect here. And yes, we can say that this point over here is the neutral point, because at this point there is no magnetic field of this one nor this one. The center in between will be a point which is a neutral point over here. So we shall now plot the non-uniform magnetic field lines of bar magnet placed in the magnetic meridian, that is along the direction in which a freely suspended magnet rests, in the following two positions. First is when the magnet is placed with its north pole pointing towards the north, and when the magnet is placed with the south pole pointing towards the north. So when the magnet is placed with the north pole pointing towards the north, so we are going to fix a sheet of white paper on a drawing board with the help of a brass pen. Mark north-south direction in the middle of the paper by keeping a compass needle on it. Draw lines along this direction and place a bar magnet on the paper along with these lines with a north pole pointing towards north. Mark that outline with a fine pencil. Now place the compass needle close to the north pole of the magnet, and looking from above, mark two pencil dots exactly in front of the two ends of the needle. Then move the compass needle in such a way that one of the needle coincides with the second pencil dot. Mark position of the other end of the needle with a dot. Repeat the process on moving the compass needle till other end of the bar magnet is reached. Join different dots to get a continuous smooth curve. Thus, one magnetic field lines is traced. Repeat the process for the same poles of the magnet, but starting from the different points, and trace out another magnetic field lines. In this manner, draw several magnetic field lines starting from the different points near the same poles of the magnet. Label each line with an arrow from the north pole towards the south pole of the magnet, or from the south pole to the north pole. Compass needle to the north pole to indicate the direction of magnetic field at that place. Now, all this what we have read is not required to learn. Neither you can understand it with what I am showing you right now. So let's see what exactly happens is we are going to plot, or we are going to trace the path of the magnetic field lines of a bar magnet, which is placed in such a way that, so first of all what you are having is a sheet of paper. In that paper you are going to mark that which is the geographical north over here. So we know that the geographical north is in that direction, and then you are going to place a needle, a bar magnet over here, such that the north pole is here and the south pole is here. So this is what you are going to do, and then you are going to do, वो हम लोग ने देखा था ना कि कैसे हम लोग ट्रेस करते हैं कि ये कंपास रखा इधर, ये डॉट किया, फिर इधर कंपास रखा, ये डॉट किया, फिर कंपास रखा, ये डॉट और ये डॉट किया, ऐसे करके you are going to trace the path of the magnetic field. So for that we will find that the Earth's magnetic field over here, which was supposed to go like this, straight over here, it is supposed to go straight over here, right? The Earth magnetic field is like this, but because of the presence of this magnet over here, what actually happens is not that it does not pass this way, but instead of that, it is going to get attracted from here. It is going to get attracted towards the pole over here. So these are going to get attracted towards the pole over here like this, and then the outermost one will be such that it just reflects like this. Okay, तो उसके बाद का जो यहाँ पे possible नहीं है, attraction possible नहीं है, like this, and the magnetic of this one will be traveling in this direction. So the north. So here it is seen that they are going to travel from. So magnetic, yeah, so this is going to travel in this direction, right? And so this also travels there, this way. And from here, they are going to emerge out like this. In this direction. And over here, you will find that the field magnet over here will be having the magnetic field like this. Of course, it will be from north to south. Okay? It will be seen that at this particular point over here and this particular point over here, these 2 points, there won't be any magnetic field available, and that is why these X points over here are called as neutral points. Okay, these are the neutral points. According, you see that this is the figure for a bar magnet when placed in such a way that the north pole of the bar magnet is pointing towards the north pole of the geographical north. Okay, north pole of the bar magnet points to geographical north. It is this figure. The next figure will be when the north pole, the south pole of the magnet is pointing to the geographical north. So this is north, and you have got this bar magnet in such a way which is like this, that it is south here and north here. As usual, this will be the different earth magnetic fields. So the earth magnetic field are like this, but over here what is going to happen is that these field lines will get affected due to the magnetic field lines of the magnet over here. So the magnetic field line over here are going to be like this. So there will be magnetic field lines here. You may draw just 3 or 4 lines. You need not draw so many lines which are there shown in the diagram of the textbook. You can just draw this line. So this is the north to south over here like this. And from here, the field lines which are coming over here, these lines will automatically get diverged like this. Okay, this is what happens to the field lines, the magnetic field lines of the earth. So magnetic field lines of the earth, they are going to get diverged in this particular way. So they are going to form divergence here. Why is that so? Because the field lines do not intersect each other, and hence what you get is the neutral points at these 2 points. These 2 points over here are the neutral points. So that is what is given in figure 10.10. That is, the magnetic field lines obtained are shown in the figure 10.9. These are due to the combination effect of the magnetic field of the magnet and the Earth's magnetic field. And from figure 10.9, it is noted that the magnetic field lines are curved in the vicinity of the magnet. They are mainly due to the magnetic field of the magnet, which is strong than the magnetic field of the Earth. As the distance from the magnet increases, the strength of the magnet due to the magnet decreases, and at distance it becomes weaker than the Earth's magnetic field, and the magnetic field lines are therefore parallel to each other at distant point. Here they are mainly due to the Earth's magnetic field. So as you go further, it will be like distance में पूरा parallel हो जाएगा. So after this, they are all going to become parallel, and that is because at distance they are going to be weak magnetic field. There are 2 points equidistant from the center of the magnet marked at X. Is 10.9 is east and west direction, where the magnetic field of the magnet and the horizontal component of the Earth's magnet are equal in magnitude, and they are in opposite directions such that they neutralize each other. These are the neutral points. A compass needle, when placed in these points, remain unaffected, and the needle rests in any direction. When the magnet is placed with the south pole pointing towards the north, so ये वाला है ये condition. In this case, the bar magnet is placed on the paper along the magnet meridian with its south pole pointing towards the north. Lines of the magnetic field are traced following the same method as described in the above. Figure 10.10 shows the magnetic field lines due to the combined effect of one, the magnetic field of the magnet, and the magnetic field of the earth. Figure 10.10, we notice that the magnetic field lines are curved in the vicinity of the magnet, and they are mainly due to the magnetic field of the magnet. So they are feel that they are maximally curved due to the magnetic field of the magnet. They are mainly due to the magnetic field of the magnet, which is much stronger than the Earth's magnetic field. As the distance from the magnet increases, the strength of the magnetic field due to the magnet decreases, and at that point, at distant points, it becomes weaker than the Earth's magnetic field. The magnetic field lines are nearly parallel straight lines from south pole to north pole at the distance from the magnet. They are mainly due to the Earth's magnetic field. Point 2, there are 2 points equidistant from the center of the magnet marked as X in figure 10.10 in the north and the south direction, where the magnetic field of the magnet and the horizontal component of the Earth's magnet field are equal in magnitude. And they are in opposite direction such that the two fields neutralize each other. At these points, the compass needle remains unaffected and the needle comes to rest pointing in any direction. These points are the neutral points. So that's why we see that this point and this point are the neutral points. So let's define the neutral points. Neutral points are the points where the magnetic field of the magnet is equal in magnitude to the Earth's horizontal magnetic field, but it is in the opposite direction. Thus, the resultant or net magnetic field at the neutral point is 0. So when the magnetic field of this one, see this is direction over here, तो ये दोनों का डायरेक्शन अलग है, इसीलिए यहाँ पे न्यूट्रल पॉइंट, यहाँ पे न्यूट्रल पॉइंट, यहाँ पे न्यूट्रल पॉइंट, यहाँ पे न्यूट्रल पॉइंट. They are opposite directions. Okay, the directions are opposite. This is going this way. This is going this way. Here also you will find that this is going down and this is going up. Here this is going up. This is going down. Okay, you can see this. The arrows over here will be like this, going inside. This is going outwards. Okay, whereas this one are going this way. So after that they come parallel, but here the point is that they are different directions. Accordingly, what we get is the neutral point. So neutral points are situated symmetrically on either side of the magnet at equal distance from the center in east-west direction. If the north pole of the magnetic field faces towards the geographical north, but the neutral points are on either side of the magnet at equal distance from the center in the north-south direction if the south pole of the magnet faces the geographical north. So these two figures are absolutely very, very, very important. You should also identify when ये figure draw करना और कब ये figure draw करना है. This figure, always remember, this is the north pole of the, south pole of the south direction of the earth is the north pole of the earth magnet. इसलिए earth magnet का direction of the तो कैसा रहेगा, direction of magnetic field कैसा रहेगा, from year to year. So it's going in the upward direction. Here also it's going towards the north. Okay, तो जब वो towards the north है तो यहाँ south में वो अंदर घुस जाएगा. वैसे against यहाँ पे north पे है तो यहाँ पे repulsion होगा. So that's how we can identify it. If a compass needle is placed at the neutral point, it remains unaffected. It comes to rest pointing in any direction because the net magnetic field at these points is 0. So that was about the electromagnetism, the first part of the chapter. Now we start with the next part of the chapter, that is electromagnetism or electromagnets and its uses, but in the next video.